Hi students, so let's start lecture 57 in our course on aerospace engineering, and today I'm going to talk about directional and lateral static stability. So these are important concepts we have to look at after we have looked at the longitudinal static stability. I'm Dr. Ranjan Ganguly. Now what we learned in the previous several lectures when we talked about longitudinal static stability is that essentially the horizontal tail plays a important role in ensuring the static stability in the pitch direction or in the longitudinal direction. And today we are going to look at the remaining two directions which involve roll and yaw motion respectively. So if you look at a typical aircraft, we now know why the horizontal tail exists, but today we are going to look at why the vertical tail is there. So essentially, I will give you a hint right now. The vertical tail is there for directional static stability, which is essentially the stability in the yaw direction. So let us look at an aircraft, and we are looking at it from the top. So this is the aircraft here. You have the center of gravity at some location, that's the CG. You have the air velocity coming from front at V infinity, and we are going to look at directional static stability. So essentially the yaw motion would be this motion here, and so we are going to look at this kind of motion. So when the aircraft is completely straight like I have shown here, there is essentially no yaw motion. So now let's presume there is a certain condition under which the aircraft moves to the right, and this is due to some disturbance. And so what happens is that the aircraft moves to the right, and therefore the velocity now comes in this manner. So if we look at the velocity coming from the front and how it impinges on the vertical tail, we can clearly see that the vertical tail is going to be at an angle theta with respect to the velocity. And so if you think back about our knowledge about airfoil aerodynamics, we know that there is going to be a force which is going to act. This is essentially the lift created by this airfoil section, and this force is going to be normal to this velocity here. So this force we will call as FVT, where VT essentially stands for vertical tail. And of course you also remember that this force is going to act at the aerodynamic center of this airfoil for the vertical tail. Now typically these airfoils are symmetric sections, so that's another thing to keep in mind. Now what this force is going to do is that it's going to create a restoring moment, because you have the moment arm, the distance between the CG and this AC here, and so the restoring moment is going to try to bring back the aircraft to its starting straight position. So essentially this is a stabilizing force which is being generated by the vertical tail. Now let's take the condition where this aircraft has yawed to the left because of the disturbance. So again what happens is that the velocity was coming like this. The velocity is coming like this as far as the vertical tail is concerned. And so the vertical tail now sees the angle theta here, and therefore it's going to generate a lift force which is perpendicular to this V infinity velocity. So this lift force again is given by FVT, where VT stands for vertical tail. It's going to act at the aerodynamic center. Now because of the distance between the CG and the aerodynamic center, there is going to be a moment which is going to be created by this force, and this moment is going to be a restoring moment which I have shown here, and therefore this restoring moment is going to try to bring the aircraft back to its straight position, which I had shown a couple of slides before. So we can see that the vertical tail plays an enormous role as far as stabilizing the aircraft is concerned whenever you pitch the or you move the aircraft in any your direction. So essentially it's going to try to bring it back to its starting position, and therefore it is essentially ensuring that the static stability is maintained. Let's take a look at the aircraft now from the side view. So we have the vertical tail here. Let us say the area of this vertical tail is S subscript Vt for vertical tail, and the distance between the center of gravity of the aircraft and the aerodynamic center is L subscript Vt here. Again, Vt stands for vertical tail. And also let us presume that as far as the wing is concerned, the wingspan is given by B and S is the area of the wing platform. So we are now going to get certain equations here. We see that restoring moment in yaw is going to be FVT into LVT, which is essentially the force that acts here into this moment arm LVT. Remember, FVT is the force I showed in the previous two slides, which is generated by the vertical tail here. Now, there is a vertical tail volume ratio very similar to the one we also looked at for the horizontal tail, and this is given by LVT SVT divided by BS. So this is essentially a non-dimensional measure which you can see here. It is going to give you an indicator about how important or how big the vertical tail contribution is with respect to the area of the wing and the size of the wing. So again, just to complete the nomenclature, B is the wingspan, that's the wing here, and S is the wing platform area. So now we know how the vertical tail plays an enormous role as far as the stability in the yaw direction is concerned, also known as the directional stability. Now we are going to look at the lateral stability, and this is the stability in the roll direction, and this is essentially guaranteed by something known as the dihedral angle. So if you look at most aircraft, I would say almost all the aircrafts you see around, typically the civilian passenger jets you see in the airports and so on, they all have this dihedral angle. So dihedral means that as far as the wing is concerned, it's not totally flat here. There is an angle like this which the wing makes with respect to the horizontal red line I have shown here, and this angle I have given by this symbol gamma. So essentially this dihedral is something very small. It will typically be a few degrees, maybe 3 degrees, maybe 5 degrees, maybe even 2 degrees. And this angle is very important as far as lateral stability is concerned. So we are going to look at that. So let us start by looking at the aircraft as it is completely in straight level flight. There is no roll here. So what's going to happen is there is going to be a lift and there is going to be a weight. And ideally they are going to be balanced if you are hanging in air and flying in cruise flight. Now let us imagine a situation where again you got hit by some disturbance and therefore you now have something known as the bank angle. So this bank angle phi is now present, and because of this the lift vector acts in this direction. The weight of course continues to act downward, and so the net result of these two forces is that there is a side force generated on the aircraft. This is given by this side force F here, which I have shown in the green. So now what happens is that because of this side force, there is a sideward motion, there is a side slip velocity which is also generated, and this hits the aircraft from the side. So this is a very important component, the side slip velocity given by V subscript S, and this is something which takes place because you have been hit by the disturbance which has created this roll motion or the bank angle. Now what this side slip velocity does is that it impinges on both the different wings, and because of the presence of the dihedral, this impact is somewhat dissimilar as far as these two wings are concerned. So if we look at the wing on this side, for example, this theta 1 is small and here the theta 2 is larger. So what happens is that here the alpha value is larger and here the alpha value is smaller, which are typically the angle of attack which the airfoil section is seeing, and the net result is that the lift L1 is greater compared to the lift L2, and therefore a restoring moment essentially develops which tries to bring the aircraft back to its starting position before it was hit by the disturbance. So essentially the dihedral plays a stabilizing role here because we have this small angle here. What is happening is that this velocity Vs or the side slip velocity is having a different impact on these two different wings. The wing which is down is going to generate more lift. The wing which goes up is going to generate less lift. Now, this is going to create this restoring moment. There are more sophisticated explanations of the importance of dihedral and so on, which we could probably do when we do a full flight mechanics course, or you can check it out in any flight mechanics book. but we can see the intuitive reason why the dihedral is very important, and it helps to maintain lateral stability. So if you look around at the aircraft, I will say that almost all the aircraft you see, certainly above 90% of the aircraft will have dihedral wings. But dihedral is not totally without its limitations. You can clearly see that dihedral would cause some issues. For example, the lift vector would be something like this. So it would not be purely vertical. If the wings were completely straight, the dihedral was zero, the lift would be completely like vertical. But now there is some horizontal component of the lift, typically when you are in pure straight level flight, which is not completely desirable. But then dihedral is something which you really need because you want to have static stability in the lateral side also, or in the roll side. Now, you will also see that there are some aircraft, a very few of them, which have something known as the anhedral. And this is the situation where you essentially have negative dihedral, or what happens is that the wings kind of hang down slightly. So I used to go to the air shows when I was in college, and I used to see some of these very big transport aircraft which have anhedral. So it seemed that because of their huge weight, these guys had somewhat drooping wings. It was like they were burdened down by the high weight they had. So if you take a look at the B-52 or some of the Antonovs, the C-5M Super Galaxy, you are going to see the anhedral here. So I'm not putting any pictures here probably because of copyright issues, but if you search for any of these aircraft in Google, you are going to certainly see the pictures and you are going to see the presence of anhedral in them. Now, what does anhedral do? It actually improves the maneuverability due to the roll situation and also lateral performance. So sometime when the aircraft are very heavy, this is something you want to do because you want the aircraft to respond in the roll direction to the various pilot inputs. So to summarize what we have learned in our very simple excursion into control and stability is that the vertical tail is something which you need for directional or yaw stability. The horizontal tail is required for longitudinal or pitch stability, and also dihedral is required for lateral or roll stability. So do remember these particular nomenclatures. Directional is in yaw, longitudinal is in pitch, lateral is in roll. I actually like to refer to them as roll, pitch, and yaw, but some of these nomenclature are coming from historical times, so they continue to be there. Now, we also should remember that there are these control surfaces which can be used to generate control motion. So essentially, we have seen that the elevators have an impact on controlling pitch motion, the rudder on controlling yaw motion, and the ailerons on controlling roll motion. If you compare it to boats and so on, you will see boats have typically got this rudder because there you need to control yaw motion. And as far as these two are concerned, the pitch and the roll, these are coming into the aircraft because the aircraft not only undergoes yaw motion, it also has the capability of roll and pitch. So this certainly makes the aircraft more sophisticated device as far as control is concerned. So that was my take on some of the basics of control. I think we are going to end this control chapter here. And if you are more interested in the aspects of flight mechanics and control, this is a very interesting and deep topic, and we can look at various things such as stability derivatives, control derivatives, and so on. Maybe I'll make a lecture on that sometime down the road, and I will see you at that point. So in the next lecture set, we are going to start looking at the space aspects of this course. So we are going to make an excursion into space mechanics. So till now we were looking at aeronautics, and now we are going to start looking at astronautics. So that is the space part of the aerospace system. So I'll end this lecture today, and I will see you in a lecture sometime soon. See you then.